Careful with these parentheses. Good. Parentheses. No, sorry, we have to start with the amount, 40,000. Parentheses for 0.03 divided by 12. Close. Open. Again. 1 plus 0.03 divided by 12 again with a caret, because this has a power, and the power is 60 months. Now come down from the power and divide by parentheses, and I need another set, another parenthesis, nope, another parenthesis, 1 plus 0.03 divided by 12, close the parenthesis, because we need to put the caret and the power is 60. That's why we need a parentheses. Come down again, -1, close the parenthesis for the denominator, and then press enter. This is what we end up paying as a monthly payment. So M equals $718.75. Let's multiply this by 60 payments. So 718.75. We're going to multiply this by 60 months to see how much more how much will the loan cost us. So we borrowed 40,000. Let's see how much are we going to give back in 60 months. So the loan will cost us $3,125 because we have to give them back the 40,000 they gave us. Not too bad, because the interest rate is good, 0.03 or 3%. So the cost of the loan is $3,125. Okay? Any questions on this? So cost, again, what was it? So cost is $3,125 for the total of 60 months for the loan. Good. Any questions?
I have a question.
Yes.
In months or years?
But this is 5 years, which is 60 months.
Okay, thank you.
And this is what it's going to be if you want 60 months or 5 years. This is the total cost for the duration of the loan. So we pay this per month. So this is the monthly payment. So per month. And then I multiply by 60. I subtracted the loan because we have to give the money back, right? And the total cost for the loan for the entire 5 years is $3,125. Is that okay? Okay, I'm moving on to page 21. So we're moving on to R.2. We were going to look at functions, graphs, evaluating functions, which we touched up on. Let's see if we need anything else. So let's say we have a function, and they're asking us to evaluate it for -3, 0, -1, 7, a plus age. And look at this. Can anyone identify this very nice formula for us? What is it? How do we call it?
Difference quotient.
Excellent. Thank you. We can't get away from it. It's calculus. It's all about the difference quotient. So please tell me if we want to look at any of these functions and determine values. I think we are okay with this and we can move on because we know how to plug it in. We put in the graphing calculator, except the g of x plus age minus g of x over age, which we covered last time. let me know. Now, when we are given graphs, how do I know which of these represents a function? Anyone remembers? I mentioned it last time briefly when we graphed the piecewise defined function. When I look at a graph, how will I know which graph represents a function and which graph I'll say, oh, no, this is not a function?
Is it
the vertical line test? Thank you very much. Let me write it, and then we'll look at the graphs. The vertical line test. So if I have something like this, let's say, I can never open this red. I'm not sure why. Okay, so let's say I have this, and let's say I have this. By the vertical line test, this is not a function. By the vertical line test, this is a function. For every x value, we only read one y value. So let's say for x equals 1, I only read y equals -1. But here, for x equals -1, for example, I read a y value and I read another y value. Not a function. Function. By the vertical line test, when we look at graphs, by the vertical line test, I can identify functions. Function, because for each x there is only one y. Not a function, because it's sufficient to show that for one x value, I read more than one y value. Not a function. So back to our graphs. Anybody would like to identify, let's say, 48. Is 48 a graph, the graph of a function, or not? Is 48 the graph of a function?
No.
No. What about 49?
Yes.
Yes. What about 52?
Yes.
Perfect. It is. Very good. We already looked at the difference quotient again. What about 55? Is 55 a function?
No.
Perfect. We already looked at how to graph a piecewise defined function. We already identified and determined and simplified the difference quotient. I'd like to look now at how we find domain and range. We talked about that as well. This is, again, just algebra review. So I'd like us to look at problems 21, you choose 21 through 32. I'd like to choose any of these problems and identify domain, range, and some values of the function at different x values or vice versa. Anyone would like to pick?
26.
We want to pick 26. Very good. So in 26, the first question is domain. So notice that these are both full points, meaning those points exist. So in order to determine the domain, I have to look at the leftmost point. I'm reading the domain from the x-axis, always. So from the leftmost point to the rightmost point. Because the points exist, I will have to use brackets. So can anyone identify the domain of number 26 for us?
Is it
Domain.
-3,
5, both
Yes.
inclusive.
Yes, negative 3 comma 5. George, is that what you wanted to say?
Yep.
Perfect. Now, can anyone identify the range? The range is read on the y-axis from the lowest y value till the largest y value.
Be 1 comma 4.
Yes, also, thank you very much, 1 comma 4, also with brackets because points exist. Now, we're not going to read from my graph, but the graph looks like this. Let's suppose now the problem is asking us to find f of 1. How do I find f of 1? It means that x is 1. X equals 1 is a vertical line. Here is 1. I draw, or I imagine I draw, a vertical line that is x equals 1. I realize that it crosses the graph of the function at a point, and I want to read the y value. This is f of 1. So now let's look at the graph. F of 1. Yes, we have to approximate. What will be f of 1? Roughly.
It's like about 2.5.
Excellent. So basically we read from the point 1 comma 2.5. So this point on the actual graph is 1 comma 2.5. Good. Now let's suppose I am asked to find x such that f of x is 3. This is a different story. This means y equals 3, which is a horizontal line. So that means I go to the graph and I draw a horizontal, or imagine I draw a horizontal line, y equals 3. I see that it crosses the graph in a point, and now I will be reading the x value for that point. So notice that these are two different things. The first one gives me x, and it's asking me to find y. The second question gives me y, and it's asking me to find x. So let's look at the actual function. Good. Approximate, or whatever you tell me, I'm happy as long as it's close. So let's find x when y is 3. What would you say?
0.
We can say 0, or it's a little bit to the left, but I'm okay with 0. So what we read from, assuming that that's the case, we read from the point 0 comma 3. One other thing that I wanted to discuss here, let's suppose I have this graph. So this is the graph of a function. I hope you agree. By the vertical line test, this is a function. And a very important question here would be x-intercepts. Intercept or intercepts if they exist. And also y-intercept. So x-intercepts or zeros. X-intercepts or zeros of the function are those points where the function crosses the x-axis. Where does it cross the x-axis? It happens that this function crosses the x-axis in 3 different points. Okay, that's fine. So I'm just going to say, I'm going to put some numbers in, -3, -1, and 5. So the x-intercepts are -3, 0 as ordered pairs, -1, 0, and 5, 0. How come? Because we know that this is y equals 0. This line is y equals 0. We discussed that last time. And we know that this line is x equals 0. It's position, and this is altitude. Y equals 0. Now, what about the y-intercept? Well, the y-intercept is where the function crosses the y-axis. Well, this function crosses the y-axis right here. And I will write, let's say, -2. So 0, -2. How come? Because this is x equals 0. Good. I would like to look at a graph on the next page, and then we'll come back to other domain situations. So here it is. Incidence of breast cancer. The following graph approximates the incidence of breast cancer per 100,000 women as a function of their age in years. Age in years is the x variable, independent. And y is, the y-axis is the incidence, so number of women with breast cancer per 100,000 women. Okay? First question, use the graph to estimate the domain. Can anyone estimate the domain, roughly? Which is basically age group. Can anyone give us the domain for this function?
25, 100.
Perfect. Now the second question is, use the graph to estimate the range. The domain clearly between 25 and 100, I completely agree. Now what about the estimate of the range?
Zero comma 450.
0, 450. I agree. From 0 to 450 roughly. It can be even 460, but that's good enough. Now, what 10-year age, and this is an extremely important question because this triggers the next steps in calculus. So let me, 5 here. I need to have a sort of a replica of this graph so I can explain. Okay, so let's read the question and then I'll explain on my graph. What 10-year age interval sees the greatest increase the greatest increase in the incidence of breast cancer? It doesn't say which 10-year age interval has the most incident. No. If that were the case, I would have chosen 75 to 85. That's where I see the highest incident, right? Between 75 and 85, I see the peak. No, the question is different. What 10-year age interval sees the greatest increase in the incident? Okay, this is our first exposure to calculus. So please pay attention. I am going to draw tangent lines. And you can say tangent lines, what for? In a moment I'll explain. So at different locations, I'm going to draw tangent lines. At this point, 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 at this point. the fastest increase of this curve, and why didn't I continue? Because this is a decrease. I don't care about the decrease. I care about the fastest increase. That's the reason why I only drew tangents on the left-hand side, where the function is increasing, then the function is decreasing. And I want to determine the fastest increase. Okay, I'm going to make some estimates. The first tangent line, I'm going to say has a slope of 3. The next one, I hope you agree, is steeper. I'm going to say that the next one has a slope of 5. The next one, I hope you agree, is even steeper. So the next one, a slope of 7. Rise over run. The next one, look what happens here. So this one starts decreasing. M equals, let's say, 5 again. The next one is even slower, so let's say M equals 3. And this one is M equals 0. The slope tells us how fast the increase is. Where and which 10-year interval sees the fastest increase in the incidence of breast cancer per 100,000 women? Of course, it's difficult to read from my graph, but now you know what we're looking for. And let's look at the graph. So imagine here's the first slope. Here's the second slope. Here's the next slope. Here's the next slope. And from this moment on, it starts decreasing again. Where is the highest incidence?
50 to 60.
Between 50 and 60. The curve grows the fastest between 50 and 60. That's the fastest increase. Here, okay. Here, okay. No, very fast. Very fast. Slower, slower, slower. It doesn't decrease anymore. Any questions on this?